Hello, everyone. I think you're able to hear me right now. Let me know if you can hear me. Hi, everyone. Welcome back again to another Global Hack Week. It's so nice to see you again after 1 month. It was a really long month. And thankfully, we are back. And it's so nice to see a lot of new folks who I've never seen before. Let's see. Hi, Twinkle Star. Hi, Tamhi. Hi, Y Combinator. Oh, wow. Y Combinator is watching us. That sounds so awesome. Gaming Theo, Dave Conrad, uh, Wong Joshua, and RBPU. Uh, Hi, Oscar. Hi, Thunderbolt. Hi, Starfigura. Starfire Go. Hi, Karuzmuxcon. Okay. So nice to see new faces right here in the stream. I think I've not seen all of you before. Uh, I was showing you like the views that I have from right here. Do you want to see like the views again? I think you should be able to see it right now. Oh, there you go. The sunset is almost going down. There you go. Nice. Now you can see it. Cool. So yeah, it's a really nice sunset. And here is Mexico City. If you haven't seen like Mexico City before, this is Mexico City. So this is real cool. It's real dope. And yeah, let's just continue with this. Oh, I'm at Mexico City right now. I'm at my working offices. Uh, Yeah, I know, right? Like that sunset looks so cool. Usually, Mexico City is like a super polluted city, but like right now, the city decided to be pretty after I don't know how much, but yeah, it has been like a lot since we have a really cool view from the city. So where's that? That is Mexico City. It is like the center of Mexico City. Like the avenue is called Reforma, and it is like one of the principal avenues here in Mexico City. Um, how high up? We're at I think 26th floor. Yeah, 26th floor plus one. Yeah, we're actually like at 27th floor or yeah, like 28, 27, something like that. So yeah, let's just begin with this. So nice to see everyone, and it's nice to see. I think Thunderbolt. I don't know if you are Hispanic or not, but it's so nice to see that someone said "hola." And yeah, let's just begin with this. Give me just 1 minute until I can show you my slides real quick. And I think you should be able to see my slides right now. Yep, you should be able to see them. Alrighty, so yeah, welcome back to another Global Hack Week. This is not a Global Hack Week of ML or AI. We're going to start with the Global Hack Week season launch. We're going to hack our first NLP app. If you don't know anything about NLP, don't worry about it. We're going to watch everything that we need to know before starting. So, yep, let's just continue. So, if you don't know me, my name is David Lazaro. You can call me David, the Dave, the Wood, however you want to call me. I'm a coach right here on MLH. I think this is like my year and a half or something like that. I've been a coach right here. I've been streaming with MLH, uh, so it has been super cool. And I was a software developer at Aspen Tech. Right now, I changed my job. I'm working in a company called Blend, and we're like a fintech. I'm working as a workflow engineer. That is like a low code position, something like that. But yeah, I'm building apps with low code tools. So this is like a new journey for me. I've never used low code things, but yeah, it is like a new journey, and I'm looking forward to be learning a lot. So yeah, I was also like a campus expert, like well, still I'm a campus expert, but maybe next month I'll be becoming a campus expert alumni. Um, I have worked at the MLH fellowship with Meta. Not, I have not worked at Meta, but I have worked at in the fellowship. There are a lot of Meta projects that you can work with. So I was once upon a time a MLH fellow with one of the Meta projects. So it was like 2 years ago, something like that. On 20, on actually it was 2 years ago. Actually, like on summer 2022, I worked on the second batch of this summer batch of the MLH fellowship, and I worked as a production engineer fellow. It's like a summer where you're learning a lot, like how to use production engineer or DevOps tools and technologies and things like that, so you can become a production engineer fellow. And after all the summer, you can apply to Meta. Like you have like you work with Meta engineers, and also you have like Meta interviewers that want you to work with them. But yeah, like it was some pandemic, so I think things got not that good for Meta. But yeah, here we are. So also I love hackathons. Hackathons are my thing. I love being a hacker. I love organizing hackathons, and I also love meeting new persons at hackathons. So I founded my first hackathon on one of the northern states of Mexico, which is called Monterrey. If you are from Monterrey or if you are from Mexico and you want to participate on hackathons, just send me a message and we're going to be talking. And yeah, currently I'm building tech startup, research tools, and more things that I cannot talk about because maybe they won't exist on the future. But yeah, let's just begin with this. Oh my God, hi Shimmery, so nice to see you again. Oh my God. How's the weather right now on your city? Like it was Vermont, right? You are based on Vermont, if I remember correctly. But yeah, I'm assuming that weather right now, like summer, Vermont is like super cool. Like going to hikes or going to a trekking or something like that would be like totally awesome. But if it is like still winter on Vermont, like I'll be not amazed at all. But yeah, let's just continue with this. So, okay, let's begin. We're going to learn what is NLP. You don't need to understand anything about machine learning, NLP, or things like that. You're going to learn all the essentials that you need today. So yeah, let's just begin with this. So first of all, what is NLP? So NLP stands for Natural Language Processing, which is a field of artificial intelligence that focuses on interaction between computers and human through natural language. The goal of NLP is to enable computers to understand, interpret, and generate human language in a way that is both meaningful and contextually appropriate. Cool. Let's just continue with this. So yeah, where can we use NLP? We can use NLP on text analysis. We can parse and analyze text that we can extract, where we can extract actually useful information, like maybe sentiment analysis or words that can mark like important context to our words, right, or to our phrases and things like that. We have like an example that where we analyze this text that has turbo service, order, previous tracking number, order, and with NLP we can extract that information to categorize each one of these words, so we can identify that maybe ordered is a order issue, or the words like terrible, furious, or terrible service are actually for understanding that the service was bad and that the client has urgent necessity for the package. Also, we can use language generation, like creating human text like text to speech, such as chatbots, machine translation, and text summarization. Also, we can use information retrieval, like we can find relevant information with large collections of text, such as search engines and document retrieval systems. Also, we can use speech recognition, so we can understand what are we actually saying by using our voice and actually processing that voice to text. So that is super cool. But before seeing like all the applications that we can use for NLP, let's understand like the basic things from NLP. And for doing that, we actually need to remember vectors. Like if you have been in a physics class, like physics 101 or something like that, you're going to remember vectors. Not actually these ones though, not the one, the villain for disabled me. These ones, these vectors that like the coordinate plane, where we have like this y and x axis, where we have like these numbers where we can identify points and things like that. And the center of this coordinate plane is at 0, 0. So yeah, a vector is something that we can actually write on the coordinate plane. Like for example, we have a point that is at 3,4, which is actually like 3 points on x-axis and 4 points on y-axis. So we can draw that the vector for this one is going to be like that, right? And we have more than 2D vector. We have like also 3D vectors, like you can see right here. Instead of having like a x and y axis, we have like an x and y and z axis, or I, j, k axis, where we can just draw vectors or draw lines or things like that. So we can understand, or we can graphicate like coordinates and directions and things like that. It gets more complicated when we want to write like better vectors that are bigger than in 3 dimensions, like 4D dimensions. Like we don't have, as a human, the capacity to understand more than 3D vectors, right? Because it is like super hard. As a human, it's difficult to perceive graphically how a vector with more than 3 dimensions look. And Oppenheimer never said that. If you have heard that, Oppenheimer said that false. But yeah, luckily we have technology. We don't have to become crazy to trying to understand like everything or all the things that more than 3 dimensions mean, right? Thankfully, we can represent numbers and vectors with just mathematical annotations. We have a workaround that we have is using a numeric representation for representing vectors too. A 4-dimensional vector is represented as an ordered quadrupole of values. Each value in the quadrupole represents a magnitude of the vector in one of the dimensions of the space it occupies. The standard notation is like this one. We have like the vector and the 2 parentheses and each one of the coordinates that we want to reply, right? And if we have an n dimension space, like right here, we can just annotate our n dimension as like this, with just like having a parenthesis. You can manage it as an array, and the array is going to have like n coordinates, right? And if you are asking yourself, why do I need to learn this to understand NLP and create ChatGPT or things like that? I don't have the answer right now, but before the answer, let's talk about words and one of the coolest games of all time called StarCraft. So imagine the following case. Let's consider a hypothetical case where we want to develop an NLP system to understand and process chat logs or comments from the game StarCraft. And we have a specialized dictionary of a StarCraft terminology. Like right here, we have some weird words that if you have never played StarCraft, don't worry about it. You don't need to understand. But as you can see here, we have a dictionary that says, for example, Terran is one of the game factions. Micro is a short micromanagement referring to the tail control of individual units. PSI Storm is a powerful protest ability. Like there are a lot of words that are kind of weird right here, right? You don't need to understand them. But the problem is that we have a lot of work and concepts, and while the dictionary increments in the terms and concepts, we need to add more words, right? This guides us to the following questions. How can we make it easy to manage this? And is there a way to make this analyzable? And the other question is, can we make computers use this to learn? Yes. Tokenization and vectorization. Tokenization is in the realm of NLP and machine learning, refers to the process of converting a sequence of text into smaller parts known as tokens. These tokens can be as small as characters, as long as words. The primary reason this process matters is that it helps machines to understand human language by breaking it down into bite-sized pieces, which are easier to analyze. As you can see here, we have the input text, quick search rush, a Terran base with 20 circlings, followed by micro of Hydralisk. And what we do is to take each one of these words And we have repeated words, we omit them, and we just put unique words into a set of words that is a tokenization output. As you can see here, we have the words quick, Circ Rush, add, Terran, base, wait, 20, etc., right? And the vectorization in the context of natural language processing is the process of converting text data into numerical vectors. This numerical form is necessary because machine learning algorithms work with numbers and not with text. So vectorization allows these algorithms to perform operations on textual data, such as classification, clustering, and sentiment analysis that we're going to do today. So as you can see here, we have like all of our data, and all of that data that we're going to use is going to be computed to just ones and zeros, like binary information that actually computers can understand. So the need to vectorize arises because although humans understand and process language naturally, machines operate in terms of numbers. So by vectorizing text, we can capture semantic and contextual information in a form that machines can actually process, right? So how can we do this? Like, how can I convert like all those words that I have on my left array or my left matrix to something that computers can actually understand? Like that is the main question, right? So this is the most simple method that we're going to watch today. It is called one-hot encoding. So it is that simple because as you can see here, how one-hot encoding works is that actually we have like on the left, you can see that we have an array of repeated words, like we have red, blue, and green. And what are we going to do is to actually create our tokenized dictionary, right? Like we did on the previous example. We use all the unique words that we're going to have in an array of words. Like here we have quick search routes, blah, blah, blah. Here we have just 3 unique words that are red, blue, and green. So we're going to convert those three words into unique columns that we're going to use on the right matrix of this example. As you can see here, we just have 3 columns, each column representing a color. And in this case, we have color red, color blue, and color green. So how can we identify each one of these words or these classes is going to be as simple as saying like, hey, from all the positions that I have right here, just if this word represents a color red, just mark it as 1, and the other ones are going to be 0. If this one is going to represent color blue, mark it as 1, and the other ones as 0. If this one represents color green, mark it as 1, and the others as 0. And we have that, right? On the first word, we have color red is active, color blue is not, color green is not. The second color blue is the one which is active. The other ones are deactivated. And on the green example, we have the same thing, right? We have 0, 0, and 1. So it is cool because we can identify multiple classes with just making an array that represents 1 and the other ones as 0, right? Cool. So following the StarCraft example, suppose that we have several texts from game logs, like player executed a Circ Rush strategy, or opponent responded to Circ Rush with a quick defense, or Circ Rush failed to penetrate Terran defenses. We want to convert this text into a numerical format using vectorization for their NLP tasks, like clustering game strategies, right? So the steps for vectorization are going to be, the first one is going to tokenize each one of the words that we're going to use, like split the text into tokens. For simplicity, let's consider that each word is going to be a token, like player executed, Circ, Rush, strategy, blah, blah, blah. The second one is building our vocabulary. In this case, we have repeated words. But in the second one, we don't have repeated words. We have just created a unique words array. As you can see here, player executed as Circ, blah, blah, blah. And the third one is to make one-hot encoding to represent each text as a vector using one-hot encoding. Its dimension of the vector is going to correspond to a word in the vocabulary. As you can see here, player executed a Circ Rush strategy is going to be our first text, like we saw right here. Player executed a Circ Rush strategy. And in our dictionary or in our vocabulary, we have the first 1, 2, 3, 4, 5, 6. The first 6 words represented as player executed a Circ Rush strategy, right? but the other ones are going to be deactivated because they don't appear in our text. So how we can do that is we can make this big array that is going to be of the size of our vocabulary, but we're just going to activate the words that actually appear on my text, and we're going to activate it based on the position of the words in our vocabulary. As you can see here in the first example, play executed as airbrush are going to be activated like the first 6 words because it's the position where they are. But opponent responded with a quick defense is going to be activated like in another way, right? Like there are just going to be ones representing the words that appear in my text. And we're going to do the same thing for the third example. So following the StarCraft example, we're going to do the same thing. Like we're just going to watch the vocabulary, then vectorize that into one-hot encoding, and we're going to do the same thing. And as you can see here, we have already created, I don't know which one is the size of this vocabulary, but an N size vocabulary, right? And how this is going to help us is that we can actually make like understanding like context and actually classifying specific words that relate to each other. Like for example, in StarCraft, we have 3 main, how can I say it? Like they're not classes, they're like, what's it called? It is, faction. It is a faction. Yeah, sorry. But yeah, we have 3 main factions. The first one is Protoss, the other one is called Zerg, and the other one is called Terrans. So maybe the Terrans have specific words that are more related than each other than the ones who are from the Protoss or the ones who are for Zergs, right? So this is cool, but we have a really big problem, right? Like, are you watching the amount of zeros that we have? What would happen if the vocabulary increases to 1 million words? We would need to use an array of space of 1 million units or numbers or something like that to just identify one word, right? That is not good at all, right? So is there a way to compress all of these zeros so we can just not make this out? And the answer is yes. It is actually called embeddings. So embeddings in the context of machine learning, particularly in natural language processing, are sophisticated means of representing words, phrases, or even entire documents as vector of real numbers. The concept of embeddings extends beyond to text to include other data types, such as images or graphs, but here we're going to focus on text embeddings. As you can see here, we have like a 3D space where we can have like different kind of context. Like the first one is going to be male and female, and you can watch that men is going to be like more in this space, like in a C space is going to be more to the left than the ones that are for representing females, right? Like men and king are more related because they are representing males, right? And females are like words like woman or queen are representing females. We have the same thing for countries and capitals. Canada is more, and it's like near to Ottawa. Turkey is going to be near to Ankara. Vietnam is going to be near to Hanoi, et cetera, right? So this allows us to create better spaces, and embeddings are just vectors that represent this data where lineal distances capture structures in the original data sets. So this data could consist of words, in which case we can call it a word embedding, but embeddings can also represent images, audio signals, and even a large chunk of structured data. So they are everywhere. You can watch them in some new cool stuff that is going, like we're still studying right now, like the transformers, the SVD matrix decomposition, layers of deep neural networks and things like that, right? Like decoders, transformers, encoders, like all this new stuff that is just going around. They're going to be using embeddings probably. So they're so important because they provide a common mathematical representation of your data. They compress your data, and also they preserve relationship with your data. Another thing is that they are the output of deep learning layers, providing comprehensible linear views of this complex thing. Um, is there any way to watch the Twitch live streams later? Yeah, if you go to Twitch and in our channel, you're going to have like a section that is called Build Videos. In that section, you can watch like all the videos or all the streams that we have been making in our Global Hug Weeks. So yep, let's just continue with this. And thank you so much, Y Combinator, for the help. So yeah, if you're desperate for just like coding already, just be patient. Embeddings are learned from data, typically through neural network models. And the idea is to train these models in such a way that words appearing in similar contexts are placed closer together in the embeddings space. And here's a step by step, like how they look right now. So in the training embeddings, in the training embeddings in the context that we're going to watch today, the context which a word appears, it is super crucial to trying to understand like data, right? Because we can have different examples than of the same words in different contexts, right? Like it is not going to be the same word. Like for example, if I use I hate not eating tacos to I hate tacos, right? Because the last word was not to so this is going to be super crucial, right? Because for models like WordSpec that we're going to watch later, the use of surrounding words to predict the current words or vice versa is super important because it encourages words that frequently appear near to each other to have similar embeddings. But like what you want you to understand is like the main difference or like the super crucial part of having the context of the words that we're using in a phrase, right? And I'm going to repeat the same example. It is not equal or it is not going to have the same context that as I say, I hate not eating tacos to I hate tacos. So once you understand that context is like super important, embeddings are going to be super easy. So we're going to have something called dimensionality reduction. So each word is represented as a vector in a high dimensional space, commonly with a few hundred of dimensions. And this space is much smaller than the vocabulary size, making the representation for more dense and efficient. This dense vector is something that you don't need to understand like today, but it's going to help us to understand like how we can understand context in these embeddings. So remember our one-hot encoding vectors? Well, we can use this, we can call these vectors as sparse vectors. And sparse vectors are called sparse because vectors are sparsely populated within information. Typically, we will be looking at thousands of zeros to find a few ones. So consequently, these vectors can contain many dimensions, often in like tens of thousands of dimensions. So that for us, for just understanding which words are appearing in our vocabulary, like that is super bad. And we have something else called dense vectors that are still highly dimensional, like 784 dimensions, but it can be more or less. But this is like less than 10,000, like it is super less. So however, its dimension contains relevant information determined by the neural network. Compressing these vectors is more complex, so they typically use memory. So we're sacrificing like the amount of time that we need to travel one array of 10,000 for a little bit more of a space, but this is actually cool. So word2vec is something that we're going to explain right now, but you can understand it as like the key part for creating our dense vectors. So although we now have superior technologies for building embeddings, no overview on dense vectors will be complete without word2vec. Although not the first, it was the first widely used dense embedding model, thanks to being very good and the release of word2vec toolkit, allowing easy training or usage of trained word2vec embeddings. And given a sentence, word embeddings are created by taking a specific word, translated to a one-hot encoding vector, and mapping it into and mapping its surrounding words through an encoder decoder neural network. Um, Density correlates with dimensions involved yet? Maybe, yeah. That can be one of the key factors. But yeah, going. I'm sorry, I get like super bad. Um, but yeah, word to vector, what it's going to do is to give it a sentence where embeddings are created by thinking specific words, like translated to one hot encoded vector, and mapping it into surrounding words through an encoder decoder neural network. That encoder decoders are like a super big thing, right? We're not going to explain that today, but what you need to understand is that they're another crucial part of the for creating our embeddings. And if you want, just give me a second. Let me show you encoder decoder architecture so you can see it a little bit more. Oh, there you go. Open link. Nope. Open image. There you go. Yeah, you should be seeing something like that. But yeah, it has like a lot of layers. It has like a lot of things that we're going to be doing like with encoder decoders. This is the architecture that transformer uses. The transformer are the ones who created like for example ChatGPT or things like that, right? Like they are crucial parts for making all this stuff, like for creating ChatGPT and previous NLP models uh, I forgot the like Bert. Sorry, like Bert. But yeah, let's just continue with this and give me just 1 minute. I think you should be able to see this. Yep. So this is the skip RAM version of word2vec, which, given a word, for example, fox, attempts to predict surrounding words, its context, and after training, we can discard the left and right blocks, keeping only the middle dense vector. This vector is going to represent the word to the left of the diagram and can be used to embed this word for downstream language models. And both scriptgram and cbow are alike in they produce like cbow is like bag of words. With bag of words it was like this thing that we created, like the vocabulary that is like a bag of words. And blah, blah, blah. Yeah, they're like in that, and they produce a dense embedding vector from the middle hidden layer of the encoder decoder network. From this, Mikolo produced the infamous king minus man plus woman is equal to queen example of vector arithmetic applied to language that we saw earlier, right? Like those examples where we have like this 3D dimensional space, and with that space we could watch like how they are related more, like how some words are more related than others thanks to these embeddings. And there are a lot of more things that we need to understand, like optimization, maths, which functions to use, and a lot of stuff that we're not going to learn today. But if you want to watch them, you can just give it a try. If you like maths, give it a try and try to get more into embeddings and NLP in the mathematical way. Okay, cool, nice story. But how are we going to generate embeddings practically? Like, I don't want to do all this math. I don't want to do all this stuff. So generating embeddings is like super easy for us right now. The transformer revolution in NLP has provided engineers with ample means to generate compressed representation or embeddings very efficiently and at a really high scale. A popular method is via the open source library Sentence Transformer, available via Hugging Face Model Hub or directly from the repo. And another one, more expensive method, is to use one of many API services that there exists, like, for example, OpenAI or Cohere or something like that. And what we usually do is to get that data set and use any of these tools to generate an embedding of our data set. And we pass that to our vectorial database or to any application that we're going to do based on that. Okay, so the one that we're going to use today is actually using Hugging Face. So if you don't have a Hugging Face account, that's the first thing that we're going to do. So, okay, enough story. Let's just start coding. All right. Until now, do you have any questions? Do you have any comments? Do you want to drink a little bit of water? Do you want to drink a little bit of coffee? Or can we start with this? Okay, I'm going to assume then we can start. Okay, so the first thing that we're going to do is actually going to. Shimmery says, sure. It says, definitely going to try this out. I use an app that attempts a sort of sentiment analysis, but their results are so skewed. It categorizes punctuation, like the dot, as negative. Then can we? Yeah, all these slides are available on my GitHub repo. I think I have it right here. This is my GitHub profile if you want to follow me or something like that. I usually use these slides and share them on one of my repos. And if not, I think I can share just with you like this prototype. Uh, if you just want to watch like these slides, you can use these slides. If you want to watch all the slides that we use in Global Hack Week, I have a repo right on my profile, and you can use them. Okay, cool. And let's start. So the first thing that we need to do is Google Hugging Face, and we're going to create a new account. So let me open this on incognito so I can show you Hugging Face.co. So, yep, we're just going to generate a new Hugging Face account. You can use the button right here, like the one that says, "Oh yeah, you're not saying it." Okay. Well, I think this should work if I do it like this way, like that. Yep. Just click into this button that says "Sign Up," and just create a new account on Hugging Face, like add your email address and your password, and then click into next. I'm going to pause my screen so I can log in to Hugging Face without filtering my email and password. And cool. Once you are there, you're going to. Oh my God! Hi, Faron. It's so nice to see you. It has been ages since I watched you. I watched you here. Welcome back, Faron. I see that you don't have any pineapple on your pizza right now. So what happened? You had a fight with pineapples or something like that? And also, big question. Chat, are you actually a pineapple in pizza team, or do you hate pineapple on pizza? Like, which gang are you? Are you pizza? Are you pineapple pizza gang, or are you no pineapple pizza gang? No, we have some pineapple gang right here. We have a lot of pineapple gang. Yeah. I'm not allowed to pineapple on pizza because I got in trouble. Yeah, 404 is usually a hater on pineapple. Oh my god, black olives on pizza are like top, like they're top tier. Okay, once you created your account on Hugging Face, you're going to see something like this. Like give me right here. Like this is your Hugging Face. Why are you not seeing my mouse? I think you're not seeing my mouse getting bigger. But yeah, you're going to see your main Hugging Face principal page. You have your profile right here if you want to create your profile or do something like that. And yeah, let's just continue with this. As you can see here, we have like a lot of things that are kind of weird, but we have this thing that is called models. On models, you can find a lot of interesting things. Like you can find model for whatever use you want. Like you want to create image classification, you have model for that. For example, we have a Pokemon classifier where we can just drag an image that we can add for a Pokemon. Like I don't know, let's just ask for Pikachu. Like for example, this one. Let's just download this and go back here and add the Pikachu face, and let's see which one categorize. Is it going to be correctly or not? And as you can see here, we have Pikachu with 93% of probabilities. And I think you should be able to see if I just zoom a little bit more. Yep, I think you should be seeing it right now. So yeah, we have a Pokemon classifier model that you can use, for example, in your web page or wherever you want to use it. And as you can see here, we have a computation time or on 0.1 seconds, and the main Pokemon that our model classified was Pikachu, right? But today we're not going to spend our time into understanding classifying models. The one we want to use is for sentiment analysis or sentence similarity. So for that, we're going to use something called sentence transformers, which are the main or the key part for us for understanding how the similarity of words actually work, right? So the source sentence is going to be, I don't know, pineapple on pizza rocks. And let's add another one that says 404 hates pineapple. And the other one that says Pharaoh loves pineapple on pizza. And if we compute this, we're going to see that there's an there's an error. Okay, this should add. This should return to us similarity for each one of the words, and the pineapple on pizza rocks is going to be more similar to Pharaoh loves pineapple on pizza, right? So this is going to be the first one. The second one is going to be 44 hates pizza, and the other ones. So yeah, we're just going to use this into one notebook that I'm going to share with you. Give me just 1 minute. And meanwhile, let me see. Let me resume the pineapple fight. I see that we have. Oh my god. Cool. We have a lot of pineapple gang right here. Wangjosia is pineapple gang. Faron's pineapple gang. Pineapple, but only if done right. Did you know that we have pineapple on tacos? There's some dish in Mexico called tacos al pastor con piña. We actually add pineapple into our tacos. Like this is called pastor meat, which is like meat, I think it's pork meat. Like it looks like a kebab. We have like a thing like right here. We call it trompo. Looks like a when you go to a kebab restaurant, something like that. You're going to see like the same thing. And but this actually is like a meat with a lot of chilies and a lot of condiments and a lot of things that are super cool, super tasty. I totally recommend it. Like it is one of the best tacos that you can try right here in Mexico. So if you come to Mexico, please, please, please try al pastor tacos. Al pastor tacos are like the best thing that you can get right here. So yeah, this is a thing. Actually, pineapple pizza is a thing. But to me, I love it, to be honest. But what I love the most is pineapple pizza. Have you ever seen like a fully pineapple pizza, like just pineapple? That looks so weird, dude. Like, that is one. Like, I think Farron would love this, and 404 would be like a totally hater. Hater's gonna hate, but for me, this is like the best pizza, right? Like, just the sweet with all this salty flavor of the pizza and with a really good pizza. Oof, oof. That would be so awesome. I mean, this one looks like so disgusting, to be honest. I'm sorry for Alan, but I would not eat this like in my life. But like something like this looks good. Like doesn't look like that bad, right? Like for example, something like this doesn't look bad at all, to be honest. This looks awful. But yeah, I think yeah, I know, right? Y Combinator. I totally agree with you. What is that? That is like the most cursed image that I've seen. Uh, haters gonna hate. Okay, yeah, let's just continue with this. Give me 1 minute until I find my notebook that I'm going to share with you. And give me 1 second until I open my collab. Collab that research that Google. Do they make al pastor pineapple tortas? I think they do. I think. Um, if you want, we can watch that later. Give me just 1 minute until I find my collab. Um, where is it? Particle center transformer. Uh, didn't we have something like this? Spectrograms. Um, I think it's this one actually. Yep, there you go. Alrighty, and I think I have right here my notebook that I'm going to share with you right here. So yeah, let's just continue with this. I think you should be able to see this right now, but let me zoom this a little bit more so you can follow along this. And let me know if this is enough zoom or if you need more zoom to this. Okay, yeah, so let's just continue. Let me share with you this collab. This is not my notebook. This is a notebook that I found in a video. It is from Saramori Kojaku. It is a video that explains a lot of how to use center transformers. And this is going to be the guide that we're going to use today for understanding center transformers, which is the main keyword or like the main part that we're going to use for understanding sentence similarity and also similarity for understanding NLP embeddings and all that stuff, right? So the first one that we're going to use, well, I'm going to wait 5 minutes until. Thank you so much, Circuit. Okay, yeah. So we're going to use this notebook to learn NLP today, right? So let me know when you are on your notebook so we can start with this. And while we wait, and please type in the chat that you're ready whenever you're ready so we can start with this. And while we wait, let's try to search what Faraon was asking for. Al pastor torta con piña. Yep, it exists. Oh boy, it exists. There you go, Faraon. You have your torta al pastor with pineapple. You said that it wasn't real. Someone said that it wasn't real. It wasn't like a thing, and it actually is. It is a thing, my boy. It is a thing. Alrighty, let's continue with this. All right, so I see that most of you are ready, so let's just begin with this. Okay, so how to use sentence transformer models. The first thing is that we're going to use sentence transformer package. We're going to use also a data set, and also we're going to use transformer packages for. Okay, yeah, no problem, Shamari. Thank you so much for joining. And yeah, let's just begin with this. We're going to use transformers because it provides a variety of pre-trained transformer-based models. And we're going to use sentence transformers to provide a lightweight wrapper for transformers and training procedures. So if this is the first time of you using Collab, don't worry about it. This is like a virtual space that you can use for running Python code. Like you have these black boxes that are represented like that for running code. So if you want to run code like this thing that says pip install sentence transformer, dataset sentence transformer, blah, blah, blah. And if this is your first time using Python, don't worry about it. You don't need to understand it like a lot. But I'm expecting to you, like you understand a little bit of the code of Python, like how to use variables, how to use operators, and things like that. What is an array, what is an object, because we're going to use a lot of them right now, right? But this is not going to be like something super complicated. But yeah, let's just begin. And what we're going to do here is we're going to use the Python package manager called pip to install the following packages: transformer and sentence transformer. So we're going to click on the play button, and um, this is going to be running in the background. So after installing all these libraries, we're going to import the model for our loading sentence transformer, right? So we're going to run this up after this one finishes. So once everything is done, and once this finishes installing transformers and all the stuff, we're going to select the transform based model for our embedding. There are more than 50,000. I'm going to say that there are more than $70,000 models or more. I don't know how much models or how many models are in Hugging Face. Oh yeah. Oh well, but this is just only for sentence similarity. Okay, so we have. Oh my god, that is a lot. We have 752,000 models. This is a lot. But for sentence similarity, we have just 5,400 models. So that is a lot too. So yeah, there are a lot of models that we can use for critical model decision, right? So the key feature of sentence transformer is fine tuning. In example, they are trained such that sentence embeddings are useful, whereas pre-trained models are trained such that word embeddings are useful. The fine-tuned models can be downloaded for the sentence transformer library, and you can also use pre-trained models from Hugging Face Model Hub, the one that we watched like before. And as a demonstration, we're going to use Firephrase Mini LM-L6 version 2, which is the model trained on various sentence pairs in Wikipedia, scientific papers, reviews, and question and answer websites. And this model is going to be downloaded by just adding a new variable called model, and this is going to be a new sentence transformer object. And that sentence transformer is going to be the one that we have right here. Model name is equal to Firephrase Mini LM-L6b2. Cool. So this method takes a sentence on, produces an array of embeddings in a NumPy way, and each row in the array is the embedding vector for a given sentence. So if we run model sentence transformer, we're going to download this model. As you can see right here, we're downloading the models from Hugging Face. So we're downloading a lot of stuff. And after it gets downloaded, we're just going to initialize a new variable, which is going to be an array of sentences. And the sentence is going to be like this. Like, this framework generates embeddings for each input sentence. The second word is sentence are passed as a list of the strings. And the third one is the quick brown fox jumps over the lazy dog. So the sentence are going to be encoded by calling model.encode. And we're going to pass that array. And we're going to print each one of the embeddings that we have into our embedding or into our sentences, right? So for each sentence and index that we have in our sentences array, we're going to print the length of embeddings of the index. And we're also going to print the sentence and the embeddings, right? So let's try to see. If we run this, we have our the length of our embedding. And as you can see here, the embeddings is of a size of 384 positions in our array. And the sentence is this framework generates embedding for each input size. And we have an embedding, or like the first 10 embeddings that we have into our embedding are like just weird numbers that we have right here. And we have like the same thing for each one of the words that we're going to use right here, right? So for now, we have just generated embeddings. And as you can see here, generating embeddings is like super easy. And we don't have to make like all this stuff, like making our one-hot encoding and making all the stuff, because Hugging Face and a lot of folks have make it easier for us, right? So we don't have to do a lot right now. There are like pre-trained models that are trained via millions or billions of parameters. So this is going to be easier for us. So the third thing that we need to do is to use semantic search. But I'm seeing that it's already 8 p.m. So um, blah, 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 blah. So what do you think if we take 5 minutes so we can just go for a little bit of water, eat a chocolate or whatever you want to do, and we'll be back in 5 minutes. That sounds good. I'm going to assume that is good for you. So I'll see you in 5 minutes. See ya. Hey, we back, we back. Hey, where you go? You should be seeing me right now. Okay, cool. Uh, let's continue with this. Let me see, and okay, let me see the comments. Might be jumping ahead, but maybe not. Then you can get an API from X Twitter to run a sentiment analysis on tweets. Yeah, you can do it. You can do that. I think not from Twitter. Like the API from Twitter has become like a little bit saucy, like since Elon is now on Twitter. But yeah, like also it is not free anymore. So I mean, you can, but it is going to do not be free, right? Um. Oh, no, nice. We have one Joshua. You're from the East Coast, right? Nice. Oh, so we have a lot of person from the East Coast right now. Okay, so welcome back. Yeah, Twitter API doesn't exist anymore. Yeah, don't worry about it. Okay. So there's a lot of East Coast person from here. Like, where were you watching us? Like, where are you watching us from? Like, are you from Vermont too, or like you're more from other states? Like, is Florida like Florida or something like that? Actually, I don't know which are the East Coast states. Let me watch a map of the United States. Uh, US map because I don't know anything about geography of the US. Like I know the Pacific states that those are the only ones that I know. I think there are like California, Oregon, and Washington, and that's all. But there are just three, so that is like super easy. But I think the East Coast has like a lot more. Like you have like the wasn't like like in Carolina on the East Coast, like North Carolina also and South Carolina. Oh, nice. We have person from North Carolina and Illinois. Okay, okay, yeah. Let's just begin with this, and let me just open this, and you should be seeing it right now. You okay? So I was just watching the U.S. states. I didn't know that Georgia was actually on the East Coast. Oh, Virginia is too, right? Is DC on Virginia? Oh wow, I didn't know that. We have Maryland, we have Delaware, Pennsylvania, New Jersey, Massachusetts, New York. Oh my God, there are a lot of states. I think I know more like the Midwest than the East Coast. Yeah, because I remember a lot like Montana, Wyoming, South Dakota, North Dakota, Minnesota, and all this stuff, right? But yeah, enough of your geography. Let's just continue with this. We were right here. Okay, yeah. So we were going to start with semantic search. So a key feature of BERT is the ability to capture semantics. To demonstrate this, let us consider a basic NLP task. You're given a pairs of sentence like he likes eating noodles and his favorite food is noodles, and you are asked to provide semantic relatedness of the given sentences. To calculate the semantic relatedness, we'll embed the given sentences and calculate the similarity. Let us consider the following sentence pairs in order of semantic relatedness. This is right by Maryland and Virginia. Oh, cool. Cool, nice. So yeah, let's just continue with this. So we are going to have a matrix of sentences, and if each array in the matrix or each row in the matrix is going to have two pair of sentences. The first one in the first row is going to be the little bird is bathing in the sink, and Birdie is washing himself in the water basin. And the last example we have is the black dog is running through the snow, and the sentence to compare is a race car driver is driving his car through the mud. So as you can see here, the first example is the most similar, but the last example is like the least similar, right? So where we're expecting is to receive less similarity from the last example and more similarity or a lot of similarity for the first one, right? So the first sentence is semantically equivalent, although no word except is and in are common. And this is a very challenging example, right? So the second sentence pair is also semantically very similar, but some details are different, and the last sentence pair is super different. So can the sentence transformer really capture semantic relatedness? Let's see. So for that, let's just run our cell right here to start our sentence pair matrix. And now where we're going to use is NumPy. We're going to use again the sentence transformer example, and we're going to use something called cosine similarity matrix, which is just a mathematical function to try to make to try to catch this the similarity or the difference of distances between vectors. Like right here, sentence similarity cosine. You can see it right here, I think. Yep. We're going to use something like this. We're going to just use mathematical. We're going to use mathematical function like a cosine, like a cosine similarity to try to use those vectors like we have right here. And I think you should be able to see it better if I just if I just open an image. What? No, I don't want it like this. Where is it? Where is it? Yep. Why can I not see it in a new tab? Why? Okay, I'm guessing that I guess that I'm going to need to just zoom it like this. And let me just give me a minute. What happened? Okay, yeah. I think now you should be able to see this. Right, so we're going to use cosine similarity to try to get these two vectors or these two sentences, like you've got mail and taken and rush hour to rush hour 2. So we can use this cosine and try to check out like which one is the cosine of each. Like we're going to use the mathematical function of the cosine similarity, so we can actually check out which one is closer to each other or what is the cosine of this, so we can check out the similarity between these two ones, right? And I think the mathematical function of the cosine similarity formula is this one. So yeah, this is the thing that we use. If you're a mathematical nerd like me, you get just check it out. If you're not, don't worry about it. You don't need to understand it. Well, you can, but the thing that you need to understand is that this is just going to be used to try to check out the similarity between two vectors, and this is going to return us a similarity, and we can use it also on 3D vectors and more vectors, right? So we're just going to use that for our formula right here. So yeah, we're going to use the similarity of these two vectors. We're going to use this function. You don't need to understand this part. You just need to understand this is going to return us the cosine similarity. And for each sentence pair in the sentence pairs, we're actually going to encode our sentence pairs. We're going to convert it on embeddings, and we're going to check out the cosine similarity of the embedding in between the vector 1 and the embedding 1 and embedding 2. And we're going to check out the similarities like this. So yeah, let's just run this out. And there you go. So the first one, the similarity is 69. Like the little bird is bathing in the sink, has a similarity of 69 to birdie is washing itself in the water basin. And the second example, two boys on a couch are playing video games, is kind of equal to two boys are playing a video game, right? So it has a similarity of 87. And finally, our list of like the last example, the black dog is running through the snow, and a race car driver is driving his car through the mud. Is like super different, right? So we have a similarity of 20. So the similarity for the first sentence is relatively high, even though only the two general words in an is are common. The second to the fourth sentences have clearly higher similarity than those of semantically less related sentence pairs, right? Like the fifth, like the sixth and the fifth example. Um, so this is cool, right? Because we have just watched how to use these, how to use mathematics and also Python to try to check out the similarity between words. And this is actually NLP. This is like the first thing that we're going to use for understanding NLP and understanding how similar a word is to another, right? And some friends and I are using we're using Collab to visualize sine wave at different points. You might like knows. Oh, that would be cool. Thank you so much. So yeah, let's continue. Semantic search with pre-trained models. So the sentence transformer make it easier for you to generate sentence embeddings with pre-trained models. Also, pre-trained models are not trained for sentence embeddings. They will capture some aspects of semantic relatedness of word. With pre-trained models, the embedding for a sentence is calculated by the average of the embedding of words in the sentence. Pre-trained models are sometimes useful because there are more than a lot of pre-trained models for various tasks, whereas the only less than 50 sentence transformer models trained for some specific task. An example is the sentiment analysis. Given a sentence, decide whether or not the sentiment is positive or negative. There's no sentence transformer model, but numerous pre-trained models for sentiment analysis. Well, I think there's one now, but yeah. Here we use a Hugging model, a model in the Hugging phase for sentiment analysis. And let's just use this model that we're going to use. Carflick Twitter Roberta based sentiment. This is a model trained with Twitter data to try to check out if we have something for understanding if the sentence has a positive sentiment or a negative sentiment, right? So we're going to download that right here with our model sentence transformer pre-trained model name. And the only thing that we're doing right now is to create a new sentence transformer with the model of Cardiff NLP Twitter Roberta based sentiment, right? So once downloaded, we can just start writing stuff in our sentences, and we can start with this, right? So the first thing that we're going to do is to create a new sentence array, which is going to have a lot of sentences like I love you, I don't like you, I know you, I like you before, although you did something good to me, I hate you. So this is super complicated, right? Once we use more and more words, we can check out that it is kind of complicated if it gets bigger, right? So our task is that given a query sentence, rank the sentence based on sentiment similarity, right? So the query is going to be, I like you. This is going to be the query sentence. We're going to have our embedding, which is going to be the encode of the query plus the sentences. And we're going to check out this cosine similarity of the embedding. And also we're going to sort our hints, our embeddings. And after that, we're going to check out the similarity of each one of those ones, right? So there you go. We have right here already like our sentiment analysis. We have given our model or our encoder the query, I like you, to the other one, try to check out if we have a similarity between sentiments. Like I like you is more similar to I love you than I don't like you, right? So this is really cool. So what will happen if I have something like I love pizza, I love pineapple. Is it with double N? Pineapple. Yep, it's. There's a Steam game called Pineapple Pizza. What? What? I didn't know that. Didn't know that. Like that is so cool. Okay, yeah, pineapple pizza. I love pineapple pizza. I don't like pineapple pizza. 404 hates pineapple pizza, and to me, pineapple pizza can be good in pizza only if it is done in a correct way. Okay, cool. And let's use the query as Pharaoh loves pineapple pizza. All right, so let's just run this again. And it's pineapple. Oh my god, sorry. Ah, you're right. Okay, sorry. Uh, Pineapple. There you go. Sorry for the typo. Pineapple, pineapple. There you go. All right. So let's see if this works. All right, it works. So the query was Pharaoh loves pineapple pizza, and Pharaoh loves pineapple pizza is super similar to I love pineapple pizza, and it is not. Well, as you can see, this is interesting because the sentence to me, pineapple pizza can be good in pizza. To me, pineapple can be good in pizza only if it is done in a correct way. It is more similar to Paran loves pineapple pizza than I don't like pineapple pizza because the sentiment is like where we checking out like the similarity is between sentiments, not actually between context, right? We're actually using sentiment analysis to try to check out if the word that we have it is positive or not, right? So the most positive one that we have right here is I love pineapple pizza, and the most negative is I don't like pineapple pizza. And as you can see here, the similarity we have is zero. Like it is negative completely. So, ta-da! We have just done our first model of NLP. So if you want to continue, you can use a fine-tuned models. You can start with this by yourself. You can use that. That collapse so you can use the interactive hands-on. So with fine-tuned models, go to sentence transformer library and find the model overview section. Copy a model name into model name and adapt the text that makes your first semantic search. With pre-trained models, go to Hugging Face Model Hub and click into a model for text classification. And in the model card of the model, copy the model name and at the top left and pass it to model name and adapt the text and make your first semantic search. So yeah, this is a handset that you can do for yourself, and you can also use fine-tune model data. So if you want to do this part, do it. If not, we can continue. So far we have used existing fine-tune or pre-trained models trained with generic text, right? However, we all have different problems and thus often want to tailor the models with our data. In the following, we will walk through how to find transformer-based models using sentence transformer architecture, right? So to start, we need to import some libraries like torch, like sentence transformer, input example sentences, blah, blah, blah. So we're just going to import all these functions from these libraries. And then we're going to define a model right here, right? So sentence transformer library provides building blocks to define model for sentence transformers. Here we construct a sentence transformer model with a pre-trained model called distill Roberta base and a merge pooling layer. And here we have all the instructions like how to define the base model, how to define the pooling layer, and how to construct a sentence transformer. Will exactly the same two sentences have a 100% similarity or the same sentiment always? If the word is the same, I think it is going to happen. But if the word varies by using something like adding a new word or adding a new verb like in or like something like that, it is going to change a lot. Or maybe not. It depends a lot of the context. And it is going to depend on which functions are we using for calculating the similarity. All because the cosine function is not the only one that we can use. There are a lot of mathematical functions that we can used for calculating the similarity between sentences. And it's going to depend also on the model that you're going to be using. Like some models may vary but than others, right? So yeah, let's just continue. So the first step is going to be define the base model, which is going to be the distill Roberta, and the max sequence line is going to be 512. Then we're going to define the pooling layer that aggregates word embeddings into sentence embedding. And as you can see here, we are going to use the word embedding model that get word embedding dimension and the pooling mode to mean. And then we're going to construct a center transformer, right? We're just going to install our new center transformer and with our word embedding model. And after doing that, the following are alternative model designs: model that produces unit norm sentence embeddings, and the other one is a model that produces more complex sentence embeddings. So after that, we just need to train our data. We're not going to do that right now because training data is going to maybe take a little bit more of time than we have right now. But after training our data, if you want, we can watch like the notebook. I think we're not going to have enough time to finish this because training data is going to take a little bit of time, and also you're going to be running your data. But yeah, let's just watch out what is going on right now, right? So the first model that produces unit norm sentence embeddings is going to call to a transformer like this Roberta base, and is going to again the first thing that we're doing is just getting our base model. Then we're adding the pool layer, and after that we're going to normalize our model. And after normalizing our model, we're just going to start our model as a center transformers model, right? And in the second one, first we have like our models that transformer, which is just our base model. Again, we have like the pooling layer, and after that we're going to use a dense model that is super different to a normalized model, right? It has different functions and all stuff. So this is going to reduce our 768 dimensional embeddings to 256 dimensional embeddings. So we're going to make our embeddings dense a little bit more, well, a lot more. And after that, we're just going to call a model. And after that, we need to train our data. We need to train our model with data, right? So to train the sentence transformer, we need pairs of sentences that are semantically similar. The sentence pair should be wrapped with input example, and all pairs should be stored in the loader. For example, we have our training examples that we have right here. Like input example is going to be my first sentence, my second sentence, another pair, and related sentence, right? And we're going to train our data loader with that. And as a toy example, here we're using physics paper that is just a data sets that consist of 5,000 pairs of paper published by American Physical Society journals, and a paper is paired with another paper when I see the sites, right? So we're just going to download that table. We're going to print the first lines of that table, and we're going to train our examples with each one of the data that we're going to extract from these pairs of papers, right? And after that, we're going to have like our example. And like after training and after seeing results and all the stuff, we need to use a loss function, which is the most critical part for performance. There are several loss function available in sentence transformer library. A common choice is triplet loss. You can read the paper if you want to understand a little bit more of the triplet loss. And the most common ones are Euclidean dot product and cosine similarity for trying to metric the similarity that each one of these words have. Here we use cosine similarity as a metric for similarity, which can be specified through distance metric argument at the loss function. So as you can see here, Y Combinator, like we talk about, there are a lot of mathematical functions. Here we have like Euclidean, dot product, and cosine, right? So this is going to be super key if you want to have different results, or if you want to watch which function gives you the more similarity or the less similarity, depending also on what you're doing, or which one is like your case of the data that you're using, or what you're trying to check, right? If you're trying to check like the sentiment, if you're just trying to check out like how similar they are or things like that, right? And after that, we're going to have a evaluator that is going to evaluate our model, and is going to contain various evaluators that are going to measure the performance improvements during the training phase. So here we are. We're just going to make two groups of center space, post pairs, and neck pairs, and it's going to compose. Post pairs is going to be composed of sentences paired by citations, and neck pairs is going to be composed by the pairs of randomly selected sentences. Then we're going to concatenate these pairs, and after that, we're just going to set up the evaluator, and we're going to train again. So this is going to take us more time. Usually, training takes like depending on the size of your data set, is going to take like from 10 to maybe 1 hour, 1 day, 5 hours, something like that. Training is like the most time consuming part of training machine learning models and NLP models, right? So after all this stuff, we're going to have a model that we can actually use to train and to use. So this is the notebook. And if you want to continue more with this, what I want you to search for is if you want to build NLP apps without having the necessity for doing all this stuff, and you just want to check out, for example, the similarity or something like that, we have a partner on the NLH called Cohere. And Cohere is a really cool NLP API or an AI platform that you can use for checking up, like for example, multiple applications, like the similarity between words, like embeddings, like generating embeddings, or like ranking similarities, etc., etc. You have like a lot of things that you can watch right here. So you have also a lot of resources if you want to learn more about LLMs or NLP or embeddings and transformers. Please check out the Developers LLM University and learn natural language processing and natural language models, right? We have the Cohere platform, introduction to large models, models overview, commands, text generation using the chat API for generating APIs that can for generating chatbots and things like that, streaming responses, predictable outputs, etc., etc., etc. Also, you have a cookbook if you want for some use cases like agents, open source software integration, search and embeddings, cloud, RAGs, summarization, others. And RAG is another thing that you can use for understanding a little bit more of uh, of chatbots or LLMs. Let me just, why is this in Spanish? Give me just 1 minute, because there you go. It should be N. What? How can I change the? Oh, there you go. This should be in English. Cool. So yeah, if you want to understand more about the NLP and things like that, please check out what is a retrieval augmented generation, what is a RAG, how to use RAGs, why they are so important, and how we can use them, right? And also check out LangChain. This is going to be also super cool for you if you want to understand more about creating applications that can be powered by AI and NLP. This is going to be a really cool resource for you for understanding more about prompts, retrievers, chats, embeddings, documents, and a lot of parsers, agents, and more stuff that you can use for creating awesome NLP and AI applications that you can use on your web pages. Also, I think there should be a lot of resources like Llama, ChatGPT, and one thing that you can use a lot if you want to create awesome AI APIs or AI applications is Fast API. If you want to learn how to create APIs with Python like super fast, check out Fast API. Fast API is a super cool resource for creating cool Python applications without having any problem. So, yep, if you want to check out Fast API and all the documentation, you can just go here on Learn. It starts into Python types, concurrency, user guides, first steps, etc., etc. So you can create your first APIs in Python and add AI and NLP to them. All right. So I think we're almost out of time. So if you have any questions, please, this is the time for asking something. If not, we can leave it right here and we can continue later. I'm going to see you at the same hour tomorrow, and let me share just with you the link of the check-in, so you can check into this. Please don't forget checking into the event right here. There you go. And I think right now in 1 hour, Jack is going to have a scribble.io a mini event. If you want to check out, uh, this, that would be awesome. Like if you want to just stay along, like be with other hackers, just draw something, be in the scribble, try to guess what are your hackers drawing right now. That would be super fun. Which service will be best to integrate into a web app? Fast API will be like the first thing that you're going to, like if you want to create like hackathon ready things or production ready things, Fast API will be the first one. So you can create your API that can actually process, like for example, inputs or things that came from the web application and that the AI needs to process. That will be something. So I think Fast API will be like the first part, and how to integrate them is going to be just integrating one API into your web page. What do you think about Streamlit and Typee for Python apps and NLP sentiment analysis? I have never used Typee, I think, but Streamlit is super cool. That is a really good resource, actually. If you want to create web pages without the necessity of um, creating a lot of code of creating a lot of things, like without the necessity of understanding a lot of web applications or JavaScript or HTML, blah 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 blah, you can use Streamlit. Streamlit is like it is Python code that generates just web pages like in less than 10 or 20 lines of code. So this is super dope. So if you want to learn more about Streamlit or how you can use Streamlit for uh, creating all these awesome web pages, like and super interactive, you can check out the gallery on Streamlit.io. Let me share with you the link so you can check out Streamlit. And also, Streamlit is one of our partners. So thank you so much, Shimari, for reminding me that. So yeah, if you want to check out this like a cheat sheet or how to use image background remover, data engineering, components, and more stuff, check out the community. Community has a lot of components that you can use right here. You can check out also LLMs that you can use, for example, like ChatGPT with memory, Quick Start app, Llama 2 chatbots, Jira, trending things that you have here. For example, a portfolio on a Streamlit would be something really dope. So here we have a portfolio. So this is super cool. So we have a summary of Mehul Gupta, which has created its portfolio right here. This is fully a Streamlit, so this looks so dope. And I would encourage you to check out what is Streamlit and how you can create also portfolios and also resources with Streamlit. So uh, yeah, don't worry about it. If you want to check out the videos on the MLH, you have the videos section on the Twitch channel, so you can check out this and all the streams that we stream right here on Twitch. Type is similar. It was an MLH partner. Oh, cool, nice. That's awesome. Blah, blah, blah. Since I am new to AI machine learning, what are things out there other than NLP? Well, you have LLMs, you have AI, you have computer vision, you have machine learning, you have sentiment analysis, like NLP. You have there are a lot of mathematics. You have data engineering, you have data analytics. It depends a lot on what you want to do. A really cool resource that you can check out also is this page called DataCamp. it has a lot of things that you can use for understanding data and machine learning and all the courses that they have. For example, they have courses for data engineering, software developer, data preparation, data manipulation, probability statistics, cloud, machine learning, generative AI, workarounds, understanding machine learning, prediction models, etc., etc. So if you want to check out and to try to learn, if you are a student and you have GitHub, your GitHub student developer pack gives you 3 free months of data camp. So please use them. Let's see. Yeah, Kaggle is a super good resource if you want to get into machine learning um, and AI. Uh, what can you do for contributing to this hackathon? I think it would be nice if you learn, like, first of all, understand a little bit more about Python, learning more about the Streamlit, and after you learn how to create your first pages, then you can use, yeah, I think you can use, yeah, can you use TensorFlow? Yeah, I think you would, yeah, you're highly probable. Yeah, you can use TensorFlow. You can use TensorFlow for sentiment analysis. But it would be good if you were get into transformers first. Try to understand a little bit more of transformers and get into get into them, understanding them more, and just try to use them. After understanding the transformers, you can go to other parts like understanding generative AI and things like that. But going again with Majanak, I mean with Barajnamit, um, please, first try to understand a little bit more about transformers. Try to understand more about the Streamlit, and after understanding about the Streamlit, you can just talk with the hackers on Discord to try to check out if someone wants to join into the hackathon of this weekend, and try to create something with a Streamlit. Maybe sentiment analysis input or a sentiment analysis page that can use the sentiment analysis model from Hugging Face that we watch in this stream and use it in that web page. That would be something really good to get for this hackathon, and it is something that is real. It is something that you can get in 2 days of learning without knowing anything. So, yep, I think generating that web page will be like a really good challenge for this weekend. So yeah, I think we don't have any more questions. So let's just continue with this. And thank you so much for being here. It was my pleasure to see you. And I don't remember if I shared with you the link of the check-in. Did I? Yep. Here's the check-in link so you can check in into this event. Please check in. And I'll see you tomorrow at the same hour. uh, Tomorrow we're going to have an introduction to Hugging Face, to trying to use Hugging Face into our web pages and to try to use to create an API that can use web sentiment analysis. I mean, that can use Hugging Face models to do some cool stuff. So, yep, we're going to do that tomorrow. And don't forget that in 1 hour, Binayak is going to have this Dribble.io media event. So it was a pleasure to see you. I'll see you tomorrow. Thank you so much for being here. My name is David, and I'll see you tomorrow. See ya. Bye.